So today we are going to see single phase fully controlled converters with RL load, that is inductive load. And for inductive load we can go for two types of operation, that is continuous current mode and discontinuous current mode. So continuous current mode is when alpha is less and the inductance value is higher, we can get continuous current mode of operation. So how we define continuous current mode of operation means, the inductance or the output current will be continuous without having zero magnitude. It's called continuous mode. And if the output current has zero magnitude, it will be discontinuous mode of operation. For that, the alpha value will be higher and the inductance value will be lesser for discontinuous mode. So in the discontinuous mode, we will study more in drives. But here we can see only the continuous mode of operation. So this is the circuit diagram and waveforms for the continuous load current. And here also we are having four thyristors, T1, T2, T3 and T4. T1 and T2 will conduct for the positive half cycle and T3 and T4 will conduct for the negative half cycle. And additionally we are having inductance, so that inductance will store some energy. So due to that, there will be some negative spikes in the output voltage waveform, and the current will have exponentially increased and exponentially decreased, and it will not be in phase with your output voltage. The output voltage and output current are not in phase, so both will have some lagging property. Since it is an inductive load, the current will lag the output voltage. So first we can see the positive half cycle, the T1 and T2 will be forward biased from 0 to pi, but we are applying the alpha, that is gate pulse at alpha, so that the conduction will start from the alpha to pi. So alpha to pi, the conducting thyristors are T1 and T2. So here T1 and T2 will be conducting. So here for positive half cycle, here it will be positive and here it will be negative. So the current will flows from positive to T1, then to L, then to resistance, then to T2, and it will return to the negative terminal of the input source. So this will be the current direction, and the inductance will store energy with positive at the upper end and negative at the lower end. So this will happen from alpha to pi. The inductance will get charged and the current will obviously flow through the T1, T2 and the load. Then at the angle pi, that is 180 degrees, the T1 and T2 will tends to reverse bias and tends to turn off, but it will not turn off since the inductance will not have the sudden change in current. So the inductance stored energy has to be dissipated before the conduction of next pair of thyristors. So from pi to pi plus alpha, the energy will get dissipated. So at the instant of pi, the inductance polarity will get reversed, that is minus over upper end and the plus over the lower end. This will happen at the instant of pi. So due to this minus and plus, already conducting thyristors, that is T2 and T1 will be conducting. So the current will flow through this and it will flow towards the source. So during the freewheeling operation, the current will flow towards the source. That is, this positive will be applied to the anode of T2 and this negative will be applied to the cathode of T1, so that the current will flow through T2 to the source, and again here also it will flow like this. So this will be the current direction during the energy dissipation period of the inductance. So here also T1 and T2 will be conducting from pi to pi plus alpha, and again pi plus alpha to 2 pi, the thyristors which will be conducting are T3 and T4. So here the thyristors will be T3 and T4 will be conducting. So here T3 and T4 will be conducting. So for T3 and T4, so here it will be negative and here it will be positive. So this from the positive line, the current will flow through the T3 and it will flow like this, and it will return to the T4 and it will return to the negative terminal of the battery. Here also the current direction will be in downward direction. So here the positive terminal is at the lower end of the source. So the current will flows from the positive terminal to T3, then to L, then to resistance, and it will return through T4 to the terminal of negative. So here also the inductance will store the energy with positive at the upper end and negative at the lower end, since the current direction is same, that is in downward direction. So positive and negative, the inductance will store the energy. So this energy storage period is up to 2 pi, that is pi plus alpha to 2 pi. The inductance will store energy during the conduction of T3 and T4. So at the instant of 2 pi, the cycle reverses so that the inductance will changes its polarity, that is minus at the upper end and negative positive at the lower end. So this minus will be applied to the cathode of T3 and this positive will be applied to the anode of T4. So due to this, the resistors T3 and T4 already conducting will still continue its conduction. So the energy storage in the inductance will dissipated through this the through this T3. So here the negative T3 is the negative is connected through the T3 and the positive is connected to through the T4. So here it will be go like this and here it will be the energy will be dissipated and it is fed back to the source. So from 2 pi to 2 pi plus alpha, the already conducting resistors T3 and T4 will be conducting and the energy will be dissipated. So here we can see the output current I0. So from alpha to pi, the energy will be increased. That is the inductance will source the energy, and pi to pi plus alpha, the inductance will dissipate the energy, and again pi to pi plus alpha to 2 pi, during the conduction of T3 and T4, the inductance will again store the energy, and again 2 pi to 2 pi plus alpha will be the energy dissipation period. So these are the firing pulses. IG1 and IG2 are the firing pulses for T1 and T2. IG3 and IG4 are the firing pulses for T3 and T4. So the next one will be the voltage across the thyristor VT1, VT2. That is T1 and T2. So the at the conduction during the conduction period of T1 and T2, the voltage across the thyristor is 0, and during the remaining period, the thyristor will be in off condition. So during that condition, it will follow the input voltage. That is the same input voltage waveform will be followed, and that is the input voltage is applied across the open switch, that is T1 and T2. So from 0 to alpha it will be in off condition, and alpha to pi it will be in on condition, and pi to pi plus alpha also it will be in on condition, and again here it will be in off condition, that is pi plus alpha to 2 pi plus alpha it will be in off condition. So during this it will follow the input voltage, and during on condition it will follow the or it will have the magnitude of 0. So 0 to alpha off condition, it will be the same as that of your input cycle. This is your input cycle. So this waveform you are getting as the VT1, VT2, and again alpha to pi plus alpha, we will have the 0 voltage since it is conducting. T1 and T2 will conduct from alpha to pi plus alpha. So here up to this, the T1 and T2 will be conducting. So the voltage across the devices will be 0, and after that, after pi plus alpha, we will have the voltage like this. So this will be your voltage across the thyristor T1 and T2. So this is the voltage across thyristor VT1 and VT2. The next one, VT3 and VT4 are the voltage across the thyristors T3 and T4. So T3 and T4 will conduct from pi plus alpha to 2 pi plus alpha, and remaining period it will be in off condition. So here it will be, this will be the conduction period, that is pi plus alpha to 2 pi plus alpha. So here the voltage will be 0, and alpha to pi plus alpha already conducting, that is T1 and T2 are conducting. So here also the T3 and T4 are off condition. So this is on time of the T3 and T4 from alpha to pi plus alpha, and pi plus alpha to 2 pi plus alpha it will be 0 since it is conducting. So from alpha to pi plus alpha it will follow the thyristors, that is it will follow the input voltage like this. So this voltage waveform will be getting the output voltage or the thyristor across voltage, and after that then from pi plus alpha to 2 pi plus alpha it will be 0. So this will be the continuous load current conduction of RL load for the single phase full bridge rectifiers. Then next one we can have for different firing angles, that is alpha is equal to 0 degrees. We will have the starting conduction at the 0 degrees, and it will last up to pi. Then again pi to 2 pi, the negative half cycle is rectified, and again 2 pi to 3 pi, the positive half cycle. So here T1, T2 are conducting, and here T3 and T4 are conducting, and again for the positive half cycle, the second positive half cycle, T1 and T2 are conducting. So the inductance, so you can see the inductance is exponentially charged and exponentially discharging. So here also it will be the charging period, and this will be the discharging period. So next one, for alpha is equal to 60 degrees, we can have the positive half cycle, and this is the energy dissipation period. This is a pi, and pi to pi plus alpha, we will have the energy dissipation period. And we can have for alpha for different ranges from 0 to 180 degrees. For alpha is equal to 0 degrees, it will have the maximum magnitude, and for alpha is equal to 180 degrees, it will have the 0 voltage magnitude. So this is the alpha is equal to 90 degrees. So here positive and negative values are equal. That is the positive value, positive area of the output voltage, and for negative area of the output voltage are equal. So this is your output voltage V naught, and this is the input voltage V in, and this is your output current I naught. So this is for alpha is equal to 90 degrees, and when alpha is equal to 120 degrees, so the conduction will be less, and the inductance store energy dissipation will be over here. So if we are increasing the inductance means, we can clearly observe that the positive area will be less when compared to the negative area for alpha is equal to 120 degrees. And this is the alpha for 150 degrees. So here this is V naught, and this is V input voltage, and this is the I naught. So these are the explanations for the bridge converters. The next we can derive the average output voltage. So the average output voltage is this symmetrical voltage waveform, that is positive and negative half cycles are equal. That is positive type of conduction and negative type of conduction. So the positive, that is from alpha to pi plus alpha, then pi plus alpha to 2 pi plus alpha, both the regions are equal. So we can have the symmetrical waveform, so that we can derive the expression for a single half cycle. That is, we can put the time period as pi. That then omega t is equal to, for the limit omega t is equal to alpha to pi plus alpha v naught d omega t. Then for alpha is equal for the limit of alpha to pi plus alpha v naught, that is, it will follow the input voltage Vm sin omega t d omega t, and Vm is taken outside since it is a constant. Then Vm by pi into, when integrating sin omega t, we will get minus cos omega t, that is from alpha to pi plus alpha. On substituting the limits, we will get Vm by pi into cos alpha minus cos pi plus alpha. We can write minus cos pi plus alpha minus of minus cos alpha, that is plus cos alpha. So we can write in reverse, that is cos alpha minus cos pi plus alpha. And we can write cos pi plus alpha is equal to minus cos alpha, so that minus into minus plus, we will get cos plus cos alpha. So it will be 2 cos alpha. So finally we will get the VDC as 2 Vm by pi cos alpha. So this is the control characteristics. We can draw it for the DC output voltage, that is average output voltage versus firing angle alpha. So for different values of alpha, we will get the different values of output voltage. So here we can see for alpha is equal to, in this expression we have to substitute for alpha is equal to 0, for cos 0 is equal to 1, so that VDC will be 2 Vm by pi. So for alpha is equal to 0 degrees, we will get the maximum value of DC average output voltage 2 Vm by pi. And for a maximum value of firing angle, that is when alpha is equal to 180 degrees, we will get the minus 2 Vm by pi. That is minus cos 180 degree will be minus 1, that is minus 2 Vm by pi. So for alpha is equal to 180 degrees, the maximum negative value is minus 2 Vm by pi. And for the alpha 30 degree, it will be 86 percentage of VDM, and it is for 60 degree, it will be 50 percentage of VDM, and 90 percentage it will be 0. So here we can substitute cos 90 degrees. So cos 90 will be 0, so that the VDC will be 0. So for cos alpha is equal to 90 degree, it will be 0 VDM, and for 120 degree it will be minus. After 90 degrees we will get the negative voltage, that is minus 0.5 that is 50 percentage of VDM, and for 150 degrees we will get minus 86.6 percentage of VDM. So up to 90 degrees we will get the positive voltage, and from 90 to 180 we will get the negative voltage. So we can have, so up to this we will have the positive voltage, that is positive VDC, and from 90 to 180 we will get negative VDC. So always the current will be positive in fully controlled converters. In dual converters only the current will be negative, so the output current will be positive for both the cases. The IDC, that is output current, will be positive. So we can have, for positive, that is from 0 to 90 degrees voltage will be positive and current will be positive, so that the product, that is power, will be positive. So the power is flows from source to the load. And for alpha is equal to greater than 90 degree to 180 degrees, the alpha VDC is output voltage is negative and current will always be positive. So the product power will be, the PDC is equal to VDC into IDC, that is for a negative voltage and positive current, the product PDC, that is power across the load, will be negative, so that we can say that the power is flowing in reverse direction, that is from load to source. So this mode of operation is called rectifier mode or rectifying mode, and this mode of operation is called inverting mode. So the inverting mode, the alpha is greater than 90 degrees. So from this we can say that from the control characteristics, by varying the triggering angle alpha, we can vary the output DC voltage across the load. So it is possible to control the DC output voltage by changing the triggering angle alpha. For triggering angle alpha in the range of 0 to 90 degrees, VDC is positive and the circuit operates as a controlled rectifier to convert AC supply voltage into DC output power, which is fed to the load. For triggering angle alpha greater than 90 degrees, cos alpha becomes negative, and as a result, the average DC output voltage VDC becomes negative, but the load current flows in the same positive direction, hence the output becomes positive. This means that power flows from the load circuit to the source side. So this is referred to as the line commutated inverter operation. So during the inverter mode of operation, alpha greater than 90 degree, the load energy can be fed back from the load circuit to the input AC source. So this is the RMS output voltage expression, so that we can have the symmetrical. So we can have for a time period of 1 by pi or 2 by 2 pi, that is symmetrical, that is 2 by 2 pi alpha to pi plus alpha V naught square d omega t. So we have to take the square and we have to take the square root, that is for calculating the root mean square value of the output voltage. So V naught will be Vm sin omega t, so Vm square sin square omega t. And taking the Vm square, that is constant outside, we have to integrate only the sin square omega t. The sin square omega t can be written as 1 minus cos 2 omega t by 2. So we can take the 2 in the 2 outside the limit. So we have to integrate only the 1 minus cos 2 omega t, that is d omega t minus integral of cos 2 omega t to the whole power of 1 by 2. So on integrating 1 we will get omega t, on integrating cos 2 omega t we will get sin 2 omega t by 2 to the limits of alpha to pi plus alpha. So on substituting omega t, the upper limit is pi plus alpha minus alpha, the lower limit is lower limit is alpha, and for here we have to substitute in the place of omega t we have to substitute pi plus alpha, and the lower limit is alpha. So on substituting this pi plus alpha minus alpha, so this will get cancelled, and sin 2 pi plus alpha minus sin 2 alpha. So sin 2 pi plus 2 alpha, so we can substitute the sin a plus b formula, sin 2 pi into cos 2 alpha plus cos 2 pi into sin 2 alpha minus sin 2 alpha. So these terms will be 0, since the sin 2 pi will be 0, so that this term will get 0, and cos 2 pi is plus 1, so that this value will be sin 2 alpha minus sin 2 alpha by 2. So plus sin 2 alpha minus sin 2 alpha, so this will also gets cancelled, so that we will get, so this term gets vanished, so we will get only the pi, and this pi will gets cancelled, and 1 by 2, that is 1 by 2 the whole power of 1 by 2, that is root 2. So we will get the V naught RMS as Vm by root 2. So this is a two quadrant converter. So that is single phase fully controlled converter is a two quadrant converter for the RL load. So here for 0 for alpha less than 90 degree, that is 0 to 90 degree, it will be control rectifier operation. For alpha greater than 90 degree, that is 90 to 180 degree, it is line commutated inverter operation. So here we can see, so this is a rectifying mode and this is the inverting mode. So here it is called as control rectifier, here it is called as line commutated inverter. So here the power will be positive, here the power will be negative. So here VDC and IDC are positive, so the power is positive. So here VDC is negative, current will always be positive, so the power will be negative. So this is the next case. Here we have included the freewheeling diode in parallel to the load. So in parallel to we are connecting the freewheeling diode means we will not get any negative spikes in the output voltage. Since for RL load we will get the negative spikes, so this will be eliminated by connecting a freewheeling diode. That is for alpha to pi, that is for alpha to pi, we will have the conduction of T1 and T2, and here also the current will flow like this, and the inductance will store the energy with upper end as positive and the lower end as negative. And during this conduction the freewheeling diode will be in reverse bias condition, since the positive is applied to the cathode of freewheeling diode and negative is applied to the positive of freewheeling diode. So this diode will be in reverse bias from alpha to pi. When at the instant of pi, the inductance will reverses its polarity, that is minus over here and plus over here. So this minus will positive, that is it is applied to the cathode of freewheeling diode, and this positive is applied to the anode of freewheeling diode. At this condition, this will comes into conduction since it is forward bias. So in this the portion, the freewheeling diode will be conducting from pi to pi plus alpha. The freewheeling diode will be conducting, and the inductance stored energy will flow like this. That is in the downward direction, and the inductance stored energy will be dissipated like this. And after the dissipation of the inductance stored energy, the next pair of resistors T3 and T4 will comes into conduction. So during this freewheeling diode, the voltage is output voltage V0 is directly short circuited by the freewheeling diode, so the output voltage will be 0. So it eliminates the negative spikes in the output side. Then from pi plus alpha to 2 pi, we will get the T3 and T4 conduction, and during that time also the inductance will store the energy. And for the 2 pi to 2 pi plus alpha, the freewheeling diode will comes into conduction, and here the power dissipation of the inductance energy will take place through the freewheeling diode. So this is the inductance charging period from alpha to pi. Then pi to pi plus alpha, by means of freewheeling diode, it will be discharging. Again T3 and T4, it will be charging, and here it will be discharging. So these are the thyristor voltages VT1, VT2, VT3 and VT4. So here the thyristors T1 and T2 will conduct from alpha to pi, that is pi to pi plus alpha. The freewheeling diode is only conducting. So the conduction period of T1 and T2 is from alpha to pi. So here the zero voltage, and pi to 2 pi plus alpha, the T1 and T2 are in off condition, so that it will follow the input voltage waveform. So from this we can have the same voltage waveform of the input voltage. So this is your voltage across T1 and T2. Similarly for VT3 and VT4, the voltage across resistors T3 and T4, it will conduct only from pi plus alpha to 2 pi. So during this period the voltage across the resistors will be 0. Remaining period it will be in off condition. So during the off condition of the resistors, the input voltage is fully applied across the both the resistors. So it will follow the input voltage. So here we can see the output voltage is same as that of your output voltage of the resistive load waveform. So that the conduction is from alpha to pi, and again pi plus alpha to 2 pi, pi to pi plus alpha, it will be zero voltage period. So for calculating the average and RMS output voltages, we will have the same as that of your resistive load. Since current only is differing, but the voltage waveform is same as that of your resistive load. So this is the average output voltage, that is VDC is equal to 1 by pi for alpha to pi Vm sin omega t, and we are taking the Vm as outside, and sin omega t integrating sin omega t, we will get the minus cos omega t for the limit of alpha to pi. On substituting upper limit and lower limit, minus cos phi plus cos alpha. Cos phi is equal to minus 1, that is minus into minus plus 1. So this will be minus 1, and minus into minus plus, that is 1 plus cos alpha. So this will be the same as that of your resistive load expression. And here also we are having the control characteristic same as that of your resistive load. For alpha is equal to 0 degrees, we will have the maximum voltage of 2 Vm by pi, that is 63.66 percentage. And for alpha is equal to 180 degrees, we will have 0 voltage. So for 180 degrees, we will have 0 voltage, and for alpha is equal to 0 degrees, we will have 2 Vm by pi. So here we will have the magnitude of 2 Vm by pi. In between values, we can have the different values of firing angle and different values of output voltage, average output voltages. Thank you.